Hi, my name is Noah Reef, and my project is stochastic domain transfer multiple kernel learning or multiple kernel boosting with an application to anomaly detection in encrypted network traffic. So as a little bit of background of what the problem is that we're trying to solve is that in cybersecurity, we would really like to be able to actually look at network traffic that's being sent to a user and be able to flag it for them about whether or not malware is being sent to them or not. However, we can't look at that data directly. There's huge privacy concerns involved, and it's just unfeasible to really look at directly what's being sent. Um, and especially in this age where most of network traffic is encrypted. And actually, according to a WatchGuard Technologies paper, they found that 91% of malware is actually sent over encrypted network traffic, which makes it even more difficult to actually look at that data in any way and to be able to flag it as having malware or not. So what do we actually do? Well, in terms of actually trying to make a machine learning model of any kind to make detections, this becomes problematic because having access to not enough data to actually train such a classifier becomes really problematic. Again, privacy concerns, and how do we even get access to all that data? So one way we could do this is, well, instead of actually dealing with looking at the network traffic that's being sent directly, let's actually look at metadata that's associated with it. So let's look at things like the destination IP, source port, destination port, the rate of traffic, things like that. That doesn't really violate us looking at the data directly, but information that can be known regardless that we can apply to creating a model and the features that we're interested in looking at when we create our model. So one thing that we can do is try to use unencrypted network traffic to train our model, because there's a lot more of that data that's readily accessible that allows us to actually train our model to be able to make predictions. So here we actually decide to use metadata that is associated with unencrypted network traffic and then try to train our model. Now, the other problem that gets posed with this is that there can be differences in the distribution and likelihood of certain data showing up between unencrypted network traffic and encrypted network traffic. So training a model solely on unencrypted network traffic may not be actually good enough for applying that same model to, let's say, just looking at encrypted network traffic. So we need to be able to bridge the gap between those differences. So even though the features are the same, the distribution may not be. And so it would actually lead to a less accurate classifier. So instead, we employ an idea known as domain transfer learning, which allows us to actually bridge the gap between these two different domains, this idea of unencrypted network traffic and encrypted network traffic, and allow us to actually use this unencrypted network traffic data to create a machine learning model that can do well on encrypted network traffic and actually flagging whether or not there's malware being sent or not. So now our approach becomes a little bit simpler. Now what we can do is take a bunch of unencrypted network traffic data, which is readily accessible, and then train our multi-kernel learning model using transfer learning, and have maybe just a tiny bit of encrypted data set samples. So really not a lot, with primarily most of it being unencrypted, to train our model, and then have it actually be able to make classifications on only encrypted network traffic data. And the idea is to try to maximize its accuracy only and solely in the encrypted network data domain. So the way we actually went about doing this is sort of a pictogram of the model. So we have an auxiliary or source data set and our target data set. So in this case, the auxiliary or the source would be the unencrypted network traffic data that we're going to kind of use as the source domain for training our model. And then the target data set would just correspond to the encrypted network traffic. That's the domain that we want our classifier to be able to, at the end of it all, be able to make really good classifiers over. So we end up kind of combining, again, most of it being from the source domain, most of it being unencrypted network traffic data that's already been labeled as either having malware or not. And we combine it together into our training data set. And basically kind of following a procedure known as sort of ADA boosting. And here it's sort of a combination of multiple kernel learning with ADA boosting. So we shorten it to multiple kernel boosting. And we end up training this classifier using, so each classifier that we make sort of during our boosting process bridges this gap between the two different domains. So one way to think of it is that we are trying to make a stronger and stronger classifier. And each time this classifier that we're slowly making better is also slowly bridging the gap between the two different domains. And so the hope is that once we get to that final really good classifier that makes really great predictions, it will actually make really great predictions as well as working really well over just encrypted network traffic data. So this is sort of just like a broad overview of the actual model that we made. And so here are some kind of preliminary results of the actual accuracy of our model. So we didn't use any sort of malware or not malware yet, but we did end up using a data set of data that was either using Tor or non-Tor related data. And we used a data set with 350 training samples, only 50 being Tor related, with 300 being non-Tor related. So in this case, the non-Tor would be our source domain and our Tor would be the target domain. So again, only a small subset of the training data was made with what we were trying to actually get our classifier to make predictions over. And then basically, we ended up having it test over samples from just the target domain and found that it had a net accuracy of 85%. So, so far it's looking pretty good. Again, these are just the preliminary results. So we are hoping still in the process of trying to make the model even better and to actually have it run. Actually, currently we are in the process of having it run over data that is specifically for malware or not malware in encrypted or unencrypted network traffic. But so far, this provides a very promising result to what the model can be capable of. So the hopes is that we can actually, once this model has been completed and we have final results over the data that we're interested in looking over, we can then have a model that, without actually waiting till any sort of thing is downloaded to a user's computer or anything like that, and without even having to look at the data directly, we can be able to actually flag that data as containing malware or not. And this can be a very useful tool for any sort of antivirus software that might be present to actually protect users sort of in a preventative way, in a way of actually preventing the problem from reaching them in the first place, and can try to handle even new types of malware that might be sent that may not even be known yet. But those are kind of future things for us to explore. And that's sort of what our project is. So thank you for watching, and yeah.